This is a session of TK Academy, which is Team Knowledge for Architects and Designers. This is a core competency course, which is a foundational course designed to equip designers with essential knowledge and skills that are critical for success. Our topic for this course is site grading and drainage design. Think of the outdoor spaces we navigate daily: parks, roads, and building sites. Each of these relies on meticulous planning and design to ensure stability, functionality, and safety. The basis of this planning lies site grading and drainage design, two critical components that influence the overall success of any land development project. In this course, we'll explain the differences between clearing, grubbing, and stripping. You'll learn how to interpret contour lines and how to determine areas of cut and fill on a grading plan. We will show you how to recognize grading stakes on a construction site and what grading information is indicated on each. We are going to identify the heavy equipment involved with earthwork operations. Finally, we'll summarize the approach toward drainage design and explain how to use the rationale method for stormwater runoff calculations. Every site design project should begin the same way, by conducting a site survey and gathering information about the existing site conditions. It is the property owner who is responsible for providing relevant and reliable information regarding the site to the design team. Therefore, it is usually the owner or client who hires a professional land surveyor to survey the site and provide the documentation to the design team. It should be noted that in most cases, professional liability insurance for architects and designers does not extend coverage to having the site survey done underneath its services, even as a subcontract. Every final site survey should contain the property's legal description that matches the current site plat recording filed with the jurisdiction having authority. This is especially important if there is any type of administrative action to amend the plat or to rezone the site as part of the project. Every site survey should include the following: the property boundaries, any easements that run through the site, existing utilities that are both above and below grade, topography, existing vegetation, and built features such as roads, buildings, fences, signs, or other prominent features on the site. Common tools that you will see professional land surveyors use are levels and transits. These are very similar but not quite the same. A level, which is also referred to as a builder's level, is used to measure heights in relation to a fixed point known as a benchmark. A builder's level serves the same purpose as a carpenter's level, a hand tool which is used to determine if flat surfaces are level or parallel to the ground plane. The builder's level has the same function, except that it can do so over a much larger area. A transit is also able to measure heights and level surfaces like that of a builder's level, but it also has the function of being able to measure vertical plumb lines or lines that are in the vertical plane perpendicular to the level surface. The example images on the right show a builder's level on top and a transit on the bottom. As you can see, these are very similar in appearance. Both are essentially low-powered telescopes that are mounted on a plate that can rotate 360 degrees. The rotating plate is then mounted on a tripod. The builder's level has a telescope which is permanently fixed to the rotating plate, and there is no ability for it to move up and down. The transit has another joint of a pivot hinge that allows the telescope to move upwards and downwards at about 45 degrees, and that is what gives it the ability to determine plumb lines. Like within most industries, the tools and technology for performing land surveys are quickly developing. Land surveys, especially over very large areas, are making use of LiDAR technology to map the existing conditions. LiDAR stands for Light Detection and Ranging. It measures distances by using a pulsed laser light and calculates the time that the light is reflected from a surface. This can be performed from aerial locations, from airplanes, or what is commonly being done now from drones. LiDAR can penetrate vegetation cover, so it is able to map and capture topographical information below a dense tree canopy. The advantage of using this technology is that it is extremely detailed and can provide a very detailed 3D virtual model of a site. Prior to beginning any work on the site, erosion control and temporary barriers must be installed in accordance with jurisdictional requirements. These include such items as silt fences, which are required around the project perimeter and downslope of any drainage areas. Drain inlet protection for both curb and area drains. Tree protection barricades for any existing trees that are to remain during the construction period. Erosion control blankets, check dams, and vehicle tracking control at the site entrance. Erosion control mechanisms are often referred to as best management practices, or BMPs. These need to be installed, maintained, and inspected on a regular basis throughout the entire construction period. Most jurisdictions will require, on any project sites larger than an acre, that a Storm Water Pollution Prevention Plan, or SWIP, be developed, submitted, and approved prior to the beginning of construction. The first steps in a site construction project are to perform the clearing, grubbing, and stripping operations. Although these are typically used collectively, the terms have separate meanings. Clearing the site means the removal of trees, brush, vegetation, and anything else that is above the surface of the ground. Grubbing, on the other hand, is the removal of things that are below the surface of the ground, such as roots, stumps, and rocks. Stripping is the removal of the top 2 to 4 inches of rich organic soil and stockpiling it somewhere else on the site to be used for later. The topsoil is where the nutrients are that plants need to thrive, and this material should not go to waste. At the end of the project, the topsoil is spread across the final grade before the plantings are installed. With the vegetation removed and the topsoil stripped off and stockpiled on the site for later use, the site is now down to the subgrade level. This is the level which grading operations should be conducted. Grading is simply defined as configuring the surface of the land by removing and/or adding earth materials, dirt, to shape the land to best suit the project and to meet the design intent. When this is done with heavy equipment such as bulldozers, graders, and dump trucks, it is referred to as rough grading. Rough grading is modifying the ground to the general shape or configuration that is being strived toward as an end state. After the rough grading is complete, workers, sometimes even using hand tools like rakes and shovels, put on the finishing touches, and this is called fine grading operations. When using large pieces of equipment and moving large volumes of earth, anything that is below grade is subject to potential damage. Most utility lines on a project site run below grade, such as water, gas, power, sewer, and communication lines. Consideration must be taken at the beginning of the project to clearly identify where these are and to mark them on the site to prevent any damage during the earthwork operations. Any damage to these utility lines could result in significant fines and penalties. There are 3 main reasons to grade a construction site. Grading reforms the land surface to make it compatible with the intended land use. The project could involve developing a building pad for a new building to be constructed, or developing a road or parking lot that has maximum grade requirements for it. The second reason is grading establishes and controls new drainage patterns. There will be surface runoff from precipitation. This needs to be controlled to direct where the runoff occurs and to prevent pooling on the site, which could lead to long-term damage. The third reason is grading helps define the aesthetics of the site. Manipulating the ground surface is one of the primary tools that designers have to shape how one experiences the site and to create a sense of place. The means of representing irregular forms and curves in the ground surface is through contours. Contour lines are imaginary lines of connecting points of equal elevation that are formed at the intersection of a horizontal plane with the ground surface. To better explain this, if you could visualize a hill and be able to slice it or cut it horizontally so that all cut points along the outside edge would form the contour line. The important thing to remember in contours is that the vertical distance between all contours must be equal. This is called a contour interval. The contour interval is typically 1 foot, but it could be greater. On larger scale drawings, the contour interval could be 5 or 10 feet. Typically on a contour map, the contour line at every 5th or 10th interval is shown as a heavier or darker line to make it easier to read. These heavier lines are known as index contours, and it makes it easier for the eye to track the continuation of the line to see the elevation on a contour map. Existing contours are shown as dashed lines on a contour map, while proposed or new contours after grading are shown as solid lines. There are 6 cardinal laws of contours. These are absolutes whenever dealing with contour lines. Number 1. Contour lines always occur in pairs. There is never a single contour line. Number 2. Contour lines may never cross. One contour line cannot cross over another contour line. Number 3. Contours have equal vertical separation. These are the contour intervals that were previously discussed. Number 4. All contour lines close on themselves or they form an enclosed shape. Number 5. Contour lines never merge or split, so you will not have a single contour line that splits and forms two or more. Number 6. The steepest slope is always perpendicular to the contour line. Most people are familiar with the basic concept of slope. Mathematically, slope is defined as the amount of change in elevation over a given horizontal distance. Or an easier way of saying this is that the slope is the rise over run. The slope can be expressed as a gradient, as a percentage such as 8% slope, a ratio such as 1 to 12 slope, or as a degree such as 4.8 degrees of slope. Some common slopes within the industry are a minimum grade of 2% slope, which is the minimum necessary to have positive drainage on a site. A pedestrian ramp that complies with accessibility requirements has a maximum of 8% slope, which is commonly known as its ratio form as 1 over 12. A parking lot typically has a maximum grade of 5% slope, which allows for adequate drainage, but not too steep so that vehicles tend not to slide or roll. A driveway has a maximum grade of about 10% slope, which is about the maximum incline that a car can reasonably surmount. As presented earlier, grading is modifying the site by either adding or removing soil to make the site conform to its new configuration. This is also referred to as cut and fill. The cut refers to an area on a site where soil is being removed, basically cutting into the slope. Fill being the opposite, an area where soil is being added. New soil material is being filled on top of an existing area. There are two other terms that define areas where soil is being either added or removed. An excavation refers to the removal of soil and material from an area, while embankment is the addition of soil onto an area to bring it up to grade. By these two techniques of cutting and filling, the site elevation can be either raised or lowered to bring it to the elevation that is desired for the new configuration. Also, as previously mentioned, existing contours are shown as dashed lines, where proposed or new contours are shown as solid lines. The cut and fill areas are indicated on a grading plan by comparing the existing contour lines to the proposed contour lines at a specific location. When the new or proposed lines extend backwards or up the hill, that indicates that it is a cut being performed. At that location where the new or proposed contour lines are extending forward or down the slope from the contour, that is a fill condition. For efficiency and economic reasons, the goal should be to obtain a balanced site where the amount of cut area is equal to the amount of fill. When there is more cut area than fill, there is excess soil, and the project is in an export condition in which soil must be hauled off from the site and disposed of. Vice versa, when there is more fill than cut, the project will need additional soil, and import soil from another site will be used in the project. Both conditions should be avoided as much as possible. A balanced site will neither require import or export of soil material, but will make use of the existing soil material on the site. Another condition to be aware of is the tendency for soils to swell when they are disturbed from their original position. This is usually caused by the introduction of air and water particles into the soil mix. The swell factor can vary greatly between different soil types. When placing fill material on a site, it cannot be done all at one time, otherwise it will be unstable. Even with compacting the top of the fill, the compaction pressures diminish through the depth of the soil material, so the lower areas will not reach the compaction level needed and settlement will occur over time. The proper technique for building up a site is to do it in a series of 6 to 12 inch layers called lifts. The site is built up in lifts because the stability of each layer depends upon the stability of the prior lift. Lifts do not always have to be the same material. In some situations, it is more desirable to have a material such as crushed rock on the subcourse levels to provide greater stability. This is often the case with road projects. The depth and compaction of each lift will depend upon a variety of factors such as soil properties, moisture content, and the compaction equipment available. Each lift is compacted separately to provide a suitable foundation for the next lift that is placed above it. In most situations, a compaction level of 95% is suitable for most structures to be built upon. Once the grading design has been developed and worked out on paper, there must be a way of conveying that information to the equipment operators in the field. This is done with grading stakes. Typically, grading stakes are wooden laths placed in the ground with survey and grading information written on it. They will convey to the equipment operator the amount of cut or fill that needs to be done at that point. On linear projects, such as roads, grading stakes are placed in a linear fashion. For an area grading project, stakes are placed in a grid across the site. One side of the grading stake will indicate what the station number is. The station number may be the grid coordinates or the distance from a certain starting point or benchmark. This example to the right shows grading stakes for a linear grading project. Grading stakes are placed along the center line of the project, so the grading stakes are marked at the top with the CL symbol, which stands for center line. The grading stakes are placed at equal distance or at points of significance, such as the beginning of a curve radius or an intersection with another road. The horizontal interval is referred to as a station and is indicated on the grading stake along with any additional horizontal distance above the typical interval spacing. For this example, the interval spacing is 100 feet. Station 5 is the fifth grading stake in sequence, which indicates that Station 5 is 500 feet from the project starting point. Most points of significance are not aligned with equal interval spacing, so the additional horizontal distance is indicated on the grading stake immediately after the station number. In this example, the distance of 50 is indicated after the station number of 5, which indicates that the linear point is 550 feet away from the benchmark along the center line of the road. Sometimes you may see the existing elevation indicated beneath the station number on the front of the grading stake. The reverse side of the grading stake will indicate the amount of cut or fill that needs to be implemented at that specific location. The amount of cut or fill will be written on the back of the grading stake with either the cut or fill symbol and the quantity recorded in feet or tenths of feet. Rough grading operations are performed with heavy equipment that can move large volumes of earth material on a project site. Each piece of equipment is used for a specific function or purpose on the job site. The equipment that is typically used for grading consists of dozers, graders, and scrapers. Dozers are tread vehicles with large blades mounted to the front. These are used for pushing or pulling earth materials for short distances. A grader is on wheels with an adjustable blade that is mounted in the center between the wheels. A grader is used for leveling, crowning, spreading, and ditching on a job site. A scraper has a blade and bucket between the wheels, which is used to scrape the top surface of the earth into the bucket for hauling long distances. Equipment used for excavations consists of backhoes and trenchers. A backhoe has a long arm with a scoop on it. It is used for extensive trenching or digging. A trencher usually has a revolving blade on it for the use of cutting shallow trenches. Transportation equipment for moving soil over long distances include dump trucks and loaders. Dump trucks obviously are for hauling and delivering over long distances or between project sites. Loaders, which have a large scoop on front, are used for lifting and loading earth materials, typically into the dump trucks. One of the primary purposes of grading a project site is to manage the stormwater drainage. Almost everywhere on the earth is subject to receiving precipitation of some type. Once precipitation reaches the ground, one of four things can happen to the water. It could evaporate back into the atmosphere. It could infiltrate into the groundwater. It could be captured and stored in a basin, or it can run off the site. When dealing with grading operations, the primary concern is with stormwater runoff. The cardinal law of stormwater drainage is that water always runs downhill. Designers must always be cognizant of the downhill condition and where the stormwater eventually discharges from the site. When sustainability is a consideration of the project, There are two aspects which stormwater management can be evaluated. Stormwater quality, which is looking at ways to filter the stormwater on site to remove some of the impurities before the stormwater is discharged. And the second means is stormwater quantity, which is reducing the amount of stormwater that is discharged from the site. Stormwater drainage areas are defined by the area water capture and are referred to as basins. A drainage basin is an area of land where all the surface water converges to a single outlet at a lower elevation. To explain this a bit more, a basin would be the area of land where the high point of the terrain, such as a ridge, would define the outer perimeter of the basin. All the water that falls on that ridge would drain perpendicular to the slope inward toward the basin into a low point where it would gather or discharge. Think of it as a large bowl-shaped formation. The basin area is often referred to as the watershed area. This can be thought of as on the macro scale, as such in the United States, where the continental divide separates the shed of water to the east or to the west into large basins that eventually discharge into either the Atlantic or Pacific Oceans. The same principle applies on a much smaller scale to just a few acres, and instead of large rivers, it applies to smaller channels. Basins and watershed areas do occur naturally, but they can also be engineered on the site to capture water. Engineered water capture basins have two purposes. A detention basin, which captures water for slow release, that typically drains out to become dry between storm events, and a retention basin, which has a permanent pool of water and it never fully drains. It should be noted that water rights differ across the United States. On the eastern part, typically there are riparian rights, which basically state that any water that flows past your property, the individual that owns that property has equal ownership to that water. However, in the West, water is less common resource and access to water is considered a public right. No one individual has right to store or claim water. In these states, it is illegal to have retention basins because that would be essentially taking water as your own and storing it on your property. This would be the case in Colorado, where detention basins are permitted, but retention basins are illegal. When precipitation falls within a watershed basin area, it will begin to make its way toward a lower elevation. The majority of this occurs at the surface plane, and this is what's called surface runoff. Surface runoff can occur in two different ways. The first being sheet flow, which is essentially the water flowing over the top ground surface plane. Water flows consistently in a thin film over the entire surface area. Eventually this water begins to gather and collect and becomes channel flow in about 300 to 500 feet. If there is no means to accommodate or encounter this channel flow, the water begins to form its own channels in the form of gullies and ruts. This is when erosion issues begin to occur. Channel flow is the concentrated flow of surface runoff in a channel or a ditch. Channel flow usually does not exceed about 800 to 1,000 feet before it enters a natural creek or river or an engineered system such as a storm sewer. All surface runoff occurs in this pattern, initially starting off as sheet flow and eventually collecting and gathering into concentrated channel flow until it reaches a point of capture or discharge. When precipitation falls within a watershed basin area, it will take time for that surface flow to reach the point of water capture or discharge. This is called the travel time. It is the time it takes the water to flow over or through any designated portion of the watershed with similar characteristics. The travel time is dependent upon how far the water is from the point of capture or discharge. Since the surface runoff distances vary across the watershed basin area, this will affect the travel time it takes for that surface runoff to reach the point of gathering or discharge. The amount of surface runoff reaching the point of discharge will begin mild at first, but then will grow in intensity. That point where the watershed basin is shedding the maximum amount of surface runoff to that point of capture or discharge is called the time of concentration. This is defined as the time it takes the surface runoff to travel from the hydrologically most distant point of the watershed or basin to the specific outlet or point of discharge. The time of concentration equals the travel time of the sheet flow plus the travel time of the channel flow within the basin area. There are numerous factors that will affect the rate and quantity of runoff from the ground surface plane. Factors such as the steepness of a slope, the type of soil, the amount of vegetation, and other varying surface conditions will affect the quantity and speed of surface runoff. For example, steeper slopes, impervious soils or surfaces such as an asphalt parking lot, or smooth unvegetated surfaces will all increase the amount of runoff. The way these varying factors are accounted for is in prescribed coefficients. Coefficients assign a prescribed value to the varying conditions that are prominent within a certain area. This is where a designer's experience and intuition come into effect. A designer makes a judgment decision on what coefficient to use based upon their knowledge of the site's characteristics. Just as there are numerous variables in the ground surface plane that affect stormwater runoff, so too precipitation events can vary greatly in type and intensity when concerning stormwater drainage. The primary factor is storm intensity. Intensity is the relationship between the storm's duration or time and the total precipitation that falls during that time. Intensity is measured in inches per hour for the time equal to that of the time of concentration. Storms that are short duration usually carry a greater intensity than those storms of longer duration. Storm intensity information comes from historical data that can be collected from multiple sources. The best source is local historical data. Most building departments will have this information available. Storm intensity information can also come from the Soil Conservation Service and from the U.S. Army Corps of Engineers. Storm intensities are gathered and recorded for each year and then charted to determine the frequency of those events. The most intense storm events that occur within a given period of time will determine the frequency or the probability of that similar storm occurring again. This is commonly known as the 10-year storm or the 100-year storm event. This is the frequency of storms occurring or the probability of a significant storm occurring within any given year that the designers can use to design for future probable events. We have described in detail each of the factors affecting stormwater runoff. Now we can use the rationale method to determine the stormwater quantity. The rationale method states that the stormwater quantity will equal the coefficient of stormwater runoff times the storm intensity times the watershed or basin area. This formula is represented as Q equals CIA. This number represents the quantity of stormwater that is at the lowest point of the basin or the point of discharge or capture. When the stormwater quantity has been identified, this then can be used to properly size drainage structures such as ditches, culverts, basins, and drains. This brings us to the conclusion of this TK Academy course on grading and drainage. If you enjoyed this course, please give it a thumbs up and leave us a comment. Also, remember to subscribe to our YouTube channel for more videos like this one and other video content from TK Architecture.